Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today we're joined by Larry Matthies, Senior Research Scientist and Head of Computer Vision in the Mobility and Robotics Division at JPL. Larry joins us on the heels of two presentations at this year's CVPR conference. The first on Onboard Stereo Vision for drone pursuit or sense and avoid, and another on vision systems for planetary landers. In our conversation, we touch on both of these talks, his work on vision systems for the first iteration of Mars rovers in 2004, and the future of planetary landing projects. Enjoy. All right, everyone, I am on the line with Larry Matthies. Larry is a senior research scientist at JPL and head of the computer vision group there within the mobility and robotics systems section, as well as an adjunct professor in computer science at the University of Southern California. Larry, welcome to This Week in Machine Learning and AI.
Thank you. It's a pleasure to be here.
Let's get started by having you tell us a little bit about your background and how you got started working on vision for intelligent systems.
Sure. I actually grew up in Canada. I studied computer graphics for a master's degree, and then I went to Carnegie Mellon for a PhD. I was interested in artificial intelligence. Back in 1981, I spent a year or so as a student of some of the AI faculty there, and I felt that in those days, the theoretical underpinnings weren't quite what I was satisfied by, so I ended up working on computer vision for robotics, which to me had a nice combination of solid underpinnings in math and physics, and some of the appeal of AI and the kind of the visual gratification of computer graphics. So it was a nice hybrid.
And how long have you been at JPL?
Since 1989, so I think that's going almost 29 years.
Oh, wow. And so what's your research focus there at the lab?
I've been working on computer vision for autonomous navigation of unmanned vehicles. That's been our main focus the whole time. The specific activities have shifted. I started working on autonomous navigation of ground vehicles, and pretty much the whole time I've been here, I've spent roughly half time working on NASA-related projects and half time working on non-NASA projects. And most of our funding here comes from government sources, so the non-NASA work has been mostly places like DARPA and the Army Research Lab. So I worked on ground vehicles. Then I started trying to address landers and orbiters on the NASA side, and I always try to complement what we do on the NASA side with related things on the non-NASA side. So in the early 2000s, I started working on vision for drones. Along the way, we've done work on vision for autonomous navigation. So those have been my main activities.
Awesome. And you recently returned from the CVPR conference in Salt Lake City, where you presented as part of a workshop on visual odometry and computer vision based on location clues. That was the title of the workshop. Can you parse that out for us? And what is visual odometry and what's the role of the location cues and all that?
So visual odometry is a technique used to estimate the motion of a camera. Usually that camera is attached to something else you care about. So in my business, that's usually a camera on the robot. So you're using the camera to track nearby features in the environment to estimate the incremental motion of the vehicle. And so it's called visual odometry as an analogy to more traditional forms of odometry based on integrating field encoders. So it's a visual dead reckoning. And the part about location clues, so visual odometry integrates forward from some starting point and it drifts. In robotics and related applications, you often want to have an estimate of absolute position and where the system is. And visual odometry doesn't do that. So you need to have some other absolute reference, and location cues could come from basically maps. to give you estimates of absolute position. In this field, there's a buzzword, simultaneous localization and mapping, which is all about maintaining the history of where you've been and updating that whole history. And if you should double back and see places you've been before, that's called loop closure, and then you can improve your estimate of that whole history. And although that loop closure doesn't necessarily tell you where you are absolutely in the world, it tells you that you're back to someplace you've been before, which is often just about as important.
And how do visual odometry and SLAM relate to, or visual odometry in particular, I guess, how does that relate to pose estimation?
So pose estimation, pose refers to the 6 degree of freedom position and orientation of a system, so the camera. So visual odometry is estimating the pose of the camera relative to some previous reference frame every time you take a picture. So pose estimation is basically part of visual odometry.
And so your talk was on vision systems for planetary landers. Can you walk us through the focus of your talk?
Sure. In planetary landers, so by planetary, we're referring to a lot of our work at JPL has been focused on landing on Mars. We did some work in the last decade on techniques for precision landing and landing hazard avoidance on the moon. And now we're working to extend these techniques to be applicable to other places like Jupiter's moon, Europa, Saturn's moon, Titan, comets and asteroids. So in landing, there's kind of a progression of capabilities that we worked on. So you want to have a good estimate of the terrain relative velocity. So in particular, the vertical velocity and then the horizontal velocity, those have to be within strict limits at touchdown or you could have a failed landing. That doesn't tell you where you are, it tells you what your velocity is. Next step is you'd like to know where you are. So that's the precision landing part. For that, you need, I was saying earlier, visual odometry doesn't tell you in absolute terms where you are. For precision landing on planetary bodies, we want to know in absolute terms where we are. So we have to have some external reference. What has been the most approachable, often we have orbiters that take high-resolution imagery from orbit of places that we want to land. And so we've been developing algorithms that will use a down-looking camera on the spacecraft as it gets close to the surface to take pictures, and then we register those pictures with the orbital imagery to get position updates. And we can use visual odometry as part of that to track features with this camera during descent to improve the velocity knowledge. So that complements the map registration to give us position knowledge. And then for places like Mars, where we've got really, really good orbital imagery, so resolution of pixels on the ground of 25 to 30 centimeters per pixel, which is good in this business, we can see almost all of the landing hazards from orbit before the lander ever gets there. So we don't really have to do onboard landing hazard detection for Mars, at least not anything we needed to do so far, because we can map the hazards before we get there, and then as long as we know where we are during descent, we can plan a trajectory to a landing site that we already know is fairly safe. For other places that we want to go that aren't as well mapped, we will need onboard landing hazard detection. So this was germane to the focus of the workshop because localization, visual odometry are important in planetary landers, and that was the theme of the workshop.
How long have we been using vision-based systems as part of our approach to trying to land things on other planets?
So the first use of vision in real time in landing was in the Mars Exploration Rover mission. So that put two rovers on Mars in basically January of 2004. Those rovers were called Spirit and Opportunity. So we had a system on that. So those rovers landed with airbags, which were deployed after a parachute phase. So we put a system on that mission that estimated horizontal velocity in the last 2 kilometers of descent to the surface, so that that velocity knowledge could be used as part of retro-rocket firing logic to reduce the horizontal velocity to make sure that we didn't burst the airbags. We used airbags for the Mars Pathfinder mission in 1997 very successfully without these techniques, but the rovers by 2003, 2004 were quite a bit heavier, and we learned some things about the winds on Mars that we didn't know before that gave us some concerns. So we added this technique to give an added measure of safety. So that was the first time vision was used in a planetary landing system in real time on board.
Tell us a little bit about the general approach that you take to solving these types of problems. You, from our conversation before getting started, it sounds like you tend to focus on model-based approaches as opposed to deep learning or data-driven approaches.
Well, so in doing computer vision for robotics, which is what this is, and especially what we do at JPL is enable missions. And so it's applied research, and you've always got, so it's applied research in contrast with basic research at universities. So we've always got a mission in mind. Those missions always have schedule and budget constraints, and the people who build those missions tend to be a little risk averse. So what we always need to do is take advantage of anything that can give us advantage. And so that inherently leads us to multi-sensor approaches. So there's been a tendency, or at least there was for a number of years in academic computer vision research, to study how much can you do with only a camera. But in our business, there's always an inertial measurement unit that gives you estimates of velocities and accelerations and angular rates. So you want to use that. And if you have prior knowledge, you want to use that. So we take advantage of all of those things. And then in the space business, space-based computing is much, much less powerful than what we can do on Earth. So we're talking 3 to 4 orders of magnitude. So you have to squeeze a lot of capability in a very small amount of compute. And we're going to places that we've either never been before, or we don't have much. We have some, but not much prior data on. So it can be hard to do learning-based approaches because you just don't have data to learn from unless you get into, transfer learning and things that are probably a little bit too cutting edge to put in a space mission yet. So we've tended to rely on a lot of geometry because that, we've got sort of a solid modeling foundation to do that. And, what we need for precision landing and landing hazard avoidance is geometry anyway. We need the geometry of the terrain. We need the position of the spacecraft, the velocity of the spacecraft. So that's not necessarily strictly geometry, but it's related. It's all with sensors that are noisy. So this is fundamentally navigation. The whole history of navigation research and development has always paid attention to modeling the noise in the sensors and propagating that into uncertainty in your state estimates, using that uncertainty in the state estimates in planning and control. So we leverage all of those techniques. And, where we can and where it makes sense, we're trying to use state-of-the-art learning methods. So those in particular apply to rovers. Once we're on the ground, we want to do terrain classification. And when we've had rovers driving in areas that we've seen from orbit, and the rovers, by now on Mars, we've accumulated, several tens of kilometers of traverse. So we've got a lot of images. So we can now start to train classifiers so that the rovers understand whether they're on bedrock or on sand, how much they might slip, how much they might sink. So we've kind of progressed from model-based techniques that exploit multi-sensor fusion with very limited computation and very limited prior data to scenarios where we do have more prior data. And we can see in the future there are things in the works that we hope will give us much more computing power in the next decade and be able to use more sophisticated techniques on board.
Can you talk a little bit about the more traditional approach where you're incorporating this multi-sensor fusion, what are the key research challenges there, and what has been how would you characterize the progression of research in that field over the past few years?
Well, in all of computer vision and robotics, we've been helped tremendously by things that basically came into the field from outside. So, it's cliche to say that advances in computing power and miniaturization and, more compute for less mass power volume and cost has been hugely enabling, but it's true. Same thing goes for inertial sensors. Same thing goes for cameras. So the whole, the invention of CMOS imagers, which was a big step in miniaturizing cameras and power for cameras. But the revolutionary progress in mobile electronics for consumer applications has spun off effectively tremendously valuable sensors, processors, and communication hardware that we can use in robotics. So that's one thing. Within our field, the field matured a lot in the time that I've been in it. So the last 30 years, 40 years actually, including grad school, in using, initially common filters and incremental batch estimation techniques, incremental bundle adjustment. So the whole simultaneous localization and mapping or SLAM literature has developed over the last 35 years or so. 3D perception has gone from, being hardly possible in the early 80s to being, routine now. So progress in algorithms for stereo vision that actually work and that are affordable, progress in other 3D sensors, Lidar in particular, being small and compact and affordable. That's made a huge difference. So in what I do for planetary exploration, there's not a lot of object recognition per se, but that's really where one of the most important research thrusts these days is in applications on Earth. And so that's an area where people tried more model-based methods for years, and that's all becoming very learning-based. So the deep learning revolution is having a big impact on how people approach those problems.
You mentioned stereo perception and the use of, I guess, image-based approaches to stereo perception as opposed to point clouds like Lidar. Can you talk a little bit about that process and how that works? I haven't thought too much about that or come across and kind of curious about that.
Okay, so I was referring to, let me call it 3D perception. So 3D perception gives you a point cloud. Lidars do that. There's multiple Lidar technology, but think of it as time of flight ranging. So you emit a short pulse of laser light and it reflects back to a detector. Mm-hmm. You measure that time of flight, that gives you range. Stereo vision gives you a point cloud by using two cameras, and you know the relative positions of those two cameras. And if you can find the image of the same object in both of those cameras, then you can triangulate where that object is in 3 dimensions. So it's just like surveyors, where surveyors look at the same point in the world from different locations, and then they can triangulate where that point is. You do that in stereo vision by having two cameras and software that for every pixel in, let's say, the left image, you find in the right image the pixel that has the projection of the same object in the world. And so if you do that at every pixel, then you build up what we call a depth map, and you triangulate, and that gives you a point cloud that is essentially the same kind of data you get from Lidar. It's got different noise characteristics. There are strengths and weaknesses for each approach, but they're both methods to give you point clouds.
Okay. Lidar is much more expensive than cameras are, and yet it's being used on a lot of autonomous vehicles. Can you maybe talk about some of the relative weaknesses of the stereo vision-based approach?
Well, so stereo vision to do this image matching, you need to have some visual texture because that's what helps you find the same point in both cameras. So if you're in an environment where you've got a lot of surfaces with very little texture, it's hard to do stereo vision-based range measurement. So think of indoor walls that are painted with very little texture, or outdoors if you're driving on a road that has, nice, clean, smooth asphalt or concrete that's not very textured. The only way you can get a range measurement to the middle of those surfaces with stereo vision is by assuming there's a continuous surface and you basically interpolate into there. Whereas with a LiDAR, you're emitting light directly. You need the surface to have enough reflectivity to bounce that light back to the sensor, but you don't need any texture per se on the surface. And because the LiDAR is emitting its own energy, it actually works better in the dark than it does during daylight. Stereo vision with, typical low-cost visible spectrum cameras, it needs an illuminator to work at night. That illuminator has limited range, so then your stereo vision system has limited range. The error, as a function of distance, the error in stereo vision-based range estimates grows as the square of the distance, whereas in LiDAR, there tends to be an analogous error characteristic, but you can design a system to have typically greater range than a stereo system. On the other hand, as you noted, stereo cameras can be quite small and cheap, and what they do for you is they give you get all of your pixels at the same point in time, and you can have a field of view that's quite large in a horizontal and vertical axis. So you can have what we call a large field of regard and get all of your data simultaneously, which matters if you're moving, because if you're moving and each pixel comes in at a different point in time, that adds complexity of how do you relate that all to, if you're trying to build a map of the world and your data is coming in at slightly different points in time, that's a harder problem. Most LiDARs have been scanning LiDARs, and so they have that issue of motion registration of the pixels. There are LiDARs called flash LiDARs that give you all of your pixels in the point cloud at the same point in time, but they typically have narrower fields of regard. So those are some of the trade-offs between the two sensors.
And you also mentioned SLAM a couple of times. How does that tend to work?
Well, if you mean does it work well or poorly, these days it works well. If you mean how does the algorithm work?
The latter.
Okay. These are all fundamentally least squares problems. So you're setting up an optimization where you've got measurements. So you've got a set of unknowns. Your unknowns are the poses for the camera for each picture and the 3D coordinates of all of your landmarks. So this whole technique has some roots in the field of photogrammetry, which is older than computer vision. And that was used for aerial surveying for, long before computer vision had become big. And in that community, they called this technique of setting up a large least squares optimization for all of the camera poses and all of the landmarks. They called that bundle adjustment because they thought of it as a bundle of rays from the camera out to all of the landmarks. And so your optimization is to find, the positions of all of these things that adjust this bundle of rays to minimize some error measure. So SLAM is basically another term for that kind of technique. And there's been a lot of progress by a number of people around the world in finding ways to do this very computationally efficiently, incrementally. So historically in photogrammetry, people would basically do this offline. They would take all of their measurements, process them offline all at once, and give you your map. But a lot of what we want to do, so in photogrammetry, they came up with this term that I think they called real-time bundle adjustment, where, suppose you take one new picture. Can you add that to your optimization and update it efficiently so you get a new map? without having to redo all of that computation. So the progress in SLAM has been finding basically linear algebra tricks to do that more and more efficiently over time, so that we can, in real time, take new data and update this network of camera poses and landmark positions. And it's used more and more sophisticated, basically linear algebra tricks to make it efficient to do this incrementally.
So maybe going back to your talk on the vision systems, your goal was to provide a review of the progress that's been made there and some of the challenges that the field has run into and perhaps remain. How far did we get in this conversation in terms of what you presented there? Are there other pieces that you can share with us, or did we cover the bulk of your talk there?
I can add a few tidbits. So, we talked about how the first vision system, real-time vision system in a planetary lander was in the Mars Exploration Rover mission that landed in 2004. We're working on another rover mission to Mars now that we expect will launch in 2020. And the plan is to have a precision landing capability in that mission, where we do what I was describing, where we have a downward-looking camera that takes pictures during descent, and on board in real time it registers templates from those pictures to orbital maps. So we're planning to use that in the 2020 rover mission to Mars. So that'll be the first time that's been done. And then looking beyond that, NASA's very interested in Jupiter's moon Europa these days. So we're studying possibilities for how would we land on Europa. So I need to be careful to say there isn't a funded mission to do this, but we're studying it. And the reason to go there is, profound scientific questions involved. One of them is, is there life elsewhere than on Earth? And if there isn't life, are there chemical precursors? Kind of on a path toward the chemistry of life. And we know that Jupiter has a liquid water ocean underneath a water ice crust. And that's kept liquid by gravitational flexing of Europa between the gravity field of Jupiter and some of the other larger moons further away from Jupiter than Europa. And we can see the effects of that in the surface of Europa, which is all broken up basically like ice flows. So the question is, in that liquid water ocean inside of Europa, could there be chemical processes that are related to the chemical processes of life, or maybe even microbial life? And that's all very speculative, but we know that one of Saturn's moons, Enceladus, it's a fairly small moon. I think it's about 500 kilometers in diameter. We've directly detected water vapor coming out of cracks in the surface of Enceladus. And we have pictures from the Hubble Space Telescope of Europa where it looks like there are water vapor plumes coming out of Europa. So that's why we want to go there. The surface of Europa is extremely rough, much rougher than any place we've tried to land on Mars. The orbital reconnaissance imagery that we're going to have of Europa is lower resolution than we have for Mars. So, if we're ever going to land there, we need an intelligent landing system. And so we're working to extend the techniques that were developed for Mars so that someday they could be applicable to Europa. Elsewhere in the outer solar system, we know there are other places that have liquid water oceans inside moons. Saturn's moon Titan is one of those. Titan is unique in the solar system outside of Earth in that there's a lot of organic molecules on the surface of Titan. The surface of Titan is 94 Kelvin, so it's really, really cold. And there are lakes and seas of liquid methane. So between those organic molecules on the surface and the liquid water ocean inside, if that liquid water ever came in contact with all the organics, there's a lot of potential interesting chemistry that could happen that could build up more and more complex organic molecules. And that might teach us some things ultimately about biology. So we're interested in landing there, and that's in some respects that's even more challenging. The terrain is not that bad, but the remote sensing data is even lower resolution than we would have at Europa, so we have to develop techniques that can cope with that. And then someday, we have also interests in Venus. There have been landers on Venus. The Soviets put landers on Venus, but they went to some of the most benign terrain there. So to go to more challenging areas on Venus is going to be hard. Venus has the densest atmosphere in the solar system by far, and the hottest temperatures on the surface by far, and it's got a very opaque cloud layer. So a very hard navigation problem on Venus, and we don't know how to solve that yet.
From a computer vision perspective, clearly, when you're looking at these different missions, there are huge system engineering types of challenges adapting to the constraints of a given mission. How do the algorithmic requirements change the way you approach each individual mission? Or rather, how does each individual mission change the way you approach the algorithms, I guess?
Yeah, so, like I said at the start, we're mission-oriented. And the way NASA works, at least the planetary science, really I think all of NASA's science, is you start with what are the scientific questions you want to answer? And then you work backwards from that to what technology do you need? And that's always guided by what can we afford? And what has an acceptable level of risk. So it's kind of case by case. We look at the science we want to do at a particular planet or moon, and then how do we do that science? And to minimize the cost and the risk, we ask, what can we leverage that we built before? So it minimizes the cost of new development and minimizes the risk that it's going to work. So you have to find a happy medium where you find an engineering solution that gives us the science within affordable cost and acceptable risk. So this is all motherhood, but that is the process.
You also did another presentation at CVPR on Onboard Stereo Vision for drone pursuit. Can you talk a little bit about that one?
Yeah, so as I was saying, we try to have complementary work going on where we have some long-term objectives for capabilities to develop for NASA, and our charter includes applying unique expertise to problems in other domains that are complementary. So, autonomous navigation of drones is one of those areas that's complementary. I can put in a plug. We're developing the first ever rotorcraft for Mars. It was recently approved to be a technology demonstration on that 2020 Mars Rover mission. So, the work that we were doing in drone pursuit or sense and avoid is complementary to those things. So, and that was funded by the Army Research Lab. So we were inspired by, if you want to have a team of cooperating drones doing anything, you don't want them to collide with each other. And in some applications, you might want to minimize communication. So you don't necessarily want the drones exchanging a lot of information. You may not have access to good external localization sensors like GPS, so you need it to all be on board. And so we thought, long term, you'd really like the drones to be able to detect each other with their own onboard sensors, so they know that they're present. They can estimate the position and velocity of other nearby drones, and then do their own path planning and control with awareness of other nearby aircraft. So our initial motivation was cooperative teams, but these techniques are equally applicable to situations where it's not cooperative, where you might want to be pursuing another drone, and that's relevant to what people call counter UAS or counter unmanned air systems. So there's a lot of concern about small drones being used for hostile purposes. So drone pursuit, when we're doing our research, just logistically, it turned out to be easier to do experiments in a pursuit scenario than in the cooperative scenario. So the paper ended up describing techniques that were relevant to both the cooperative team scenario and the pursuit scenario, but all of our testing was in the pursuit scenario. And then the stereo vision aspect comes back to our earlier discussion about the relative pros and cons of stereo vision versus Lidar. So here you've got very limited payload weight and power capacity on small drones. So if we can do something with cameras, especially if those cameras can give us a very wide, instantaneous field of regard in horizontal and vertical axes, you just can't match that with a LiDAR these days. And these are both techniques that measure 3D range, and through that you can estimate velocity of the other aircraft. So it's quite handy if you actually know the 3D position and velocity of the other aircraft. So we started with techniques, in particular stereo vision, that would give us that. Those do have range limits, so we can only see other aircraft, some limited distance away, 10, 15, maybe 20 meters at the outside with our current cameras. So this was the first paper to show that this was possible in a fully integrated fashion, outdoors, without the aid of external position sensing sensors. There needs to be extensions to be able to see other drones further away. Stereo vision is probably not going to cut it for that, so that probably requires techniques that can use a single camera. Those required more work to develop and test than was within the scope of our paper.
And from the algorithmic perspective, is the system used here primarily a composition of some of the things that we've already talked about, or are there other techniques that are specific to this system that might be interesting to explore?
Well, the work in this paper was mostly a composition of techniques we've already talked about. So, in some respects, it's analogous to the constraints we have in space because onboard computation is fairly limited. It's a lot more than we have in space, but it's still pretty limited. So we were using simple techniques to do reliable 3D perception at short range that let us do a first demonstration of this capability. One of the questions I was asked was, could you use deep learning to detect the other aircraft? It's a very good question. We had not yet tried that for lack of training data, but that's certainly conceivable. Another thing that could be used is basically difference imaging. So, a standard technique in surveillance with stationary cameras is just to take, pictures over time and subtract them and look at what's changed. And that lets you pick up things that are moving around the camera. But that's harder to do when the camera itself is moving. And so that was one of the complexities that was out of scope of this work. But another approach to detect moving drones from a drone that itself is moving is background subtraction. But then you have to do motion compensation for the motion of your own drone. That's something to look at in the future.
In the paper itself, you showed standard black and white images, but then also these multicolored images, look like some kind of spectral type of image or something. What are those?
I'm thinking you're probably referring to what we call depth maps. So, yeah, that's a false color illustration of the range at each pixel. So when we do stereo vision, we get an estimate of range at each pixel. A simple way to visualize that is just to color code the range and then show that as an image.
Got it. And so this work that you did, this was a full end-to-end system, not just it wasn't a simulation. You actually put this on a drone and put it out in the wild. Is that right?
That is right.
How did it do?
Well, it did quite well. We tested it, on the campus of JPL and on the campus of one of our sponsors. This problem is a lot easier if the other drone you're looking at is silhouetted against the sky. Then it's actually a very easy problem. So it's much harder if the other drone you're looking at is seen against what we call background clutter. So, if it's below the horizon, essentially. So if you're seeing it against trees or buildings or ground, and that changes over time, it becomes much harder if you look toward the sun, because the sun causes all sorts of glare artifacts in the image. And we found that a key advantage of our technique is that it's pretty robust to those issues, because the fact that we're using 3D perception means as long as the drone is within range, we're not fooled by background clutter, because we can segment that 3D object from the background using the point cloud data. And when we look toward the sun and there are artifacts in the image, unless things get really, really bad, we can often still do 3D perception that is adequate to track the drone. And since we've, let's say before you turn directly at the sun, you had a 3D model. You had a model of the position and velocity of the other drone from previous images. So you can do prediction for a short amount of time, if you're blinded by the sun, and then probably recover track because you've got that knowledge, model-based knowledge that you can use for prediction. So it worked pretty well.
And how do you measure the performance of the system? Do you kind of go through after the fact and measure maybe distance from where the drone thought the thing it was supposed to be following was, and compare that to some error function, or is there some automated way that you're able to measure performance?
So, that's an excellent question. You always need some kind of ground truth to measure performance. In our case, we manually labeled the images. So we put bounding boxes around the drone. Another way to do it would be if we had, an external sensor that told us where everything is. So if we had GPS, for example, on both aircraft, you could use that to give position knowledge. And in this case, I think we relied on manual labeling. We didn't have the sensor infrastructure finished to do that all with GPS. But that would help automate things.
Well, great. Larry, this was a really interesting conversation. I appreciate you taking the time to share with us what you're working on.
Well, thank you for the time to talk about it. I appreciate that.
Thanks. All right, everyone. That's our show for today. For more information on Larry or any of the topics covered in this episode, head over to TWiMLAI.com/talk/170. If you're a fan of the pod, we'd like to encourage you to pop open your Apple or Google Podcast app and leave us a 5-star rating and review. Your reviews go a long way in helping new listeners find the show. As always, thanks so much for listening, and catch you next time.